This will be the last example on determining the reflection of a certain point along a certain line. And this time our line is expressed in terms of L is equal to P plus the direction vector V. In this case, our P is actually identified as 3, -2. Our X is actually -1, -5. And the vector V is given as 1 and -6. So we can actually solve the reflection automatically if we are going to follow the formula for the reflection of point X along line L, given as X minus twice the inner product of X minus P and the normal vector, specifically unit normal vector, times the unit normal vector. So already have our X, already have a certain P, but we don't have the unit normal vector. So using this vector here, we can of course automatically get the unit normal vector. We know that for our V vector identified as V sub 1 and V sub 2, our normal vector, not yet the unit normal, but the normal vector is actually negative V sub 2 and V sub 1. This would be our V sub 1, so our normal vector here would be 1, and the first component is the negative of this, so that's positive 6. This is the normal vector for the given line. Of course, it could also be presented in this manner. It's just that we were been using this to differentiate that from any point. But this time, let me return to this notation as we're also going to integrate that in our formula. Now, we can already solve it if you would like to. But I would like to insert here another important concept or important aspect, because as we would like to solve, and if it's actually not a time pressured examination, you can do this. Because you would like this, would like you to check your process, or this could help us verify whether your answers are correct or not. If we're going to have here a graph. Now, if you don't like this, you can of course skip this and reach to that point of automatically solving for the reflection. But for those some of us here who would like to see the graph, I'm going to present it in this manner. Let me plot the X at -1, considering that each grid is 1, and -5, 1, 2, 3, 4, and 5. This is our X, -1, -5. Our point P is at 3 and -2. This is our point P. Okay, so 3 and -2. Our X should be reflected along a line that would contain point P. But at this point, we don't know the line P, because it could be line P, the line containing point P, because it could be like that, it could be like this, it could be like that. So depending on its form, so we will have different reflections as well. Again, you can solve for the reflection immediately, but for the purpose of this, allow me to continue. Okay, so in short, let me try to graph really the line so that we can actually come up with a better illustration or connection with all of the processes. Using this, by the way, using this here, by the way, I haven't provided yet the normal vector, right? So let me return first to the unit normal vector, because the normal vector will not be applied here. It's a unit normal vector. So the unit normal vector, allow me to return to this, is the normal vector over the length of the vector. The length of the said vector is the square root of the square of the sum of the squares of the quantities, 6 squared plus 1 squared. So you have here 36 plus 1. So your length is square root of 37. So your unit normal vector is 6 and 1 over square root of 37, or you will have here 6 over square root of 37 and then 1 over square root of 37. So this would be used here. Again, we can automatically solve for that, but allow me to continue with the graph. As we talk about the graph, we can actually talk about this here, because the normal vector is actually composed of A and B coefficients for our equation in the form AX plus BY plus C is equal to 0. So our A is 6 and our B is 1. So we can actually have here 6x plus 1y plus C is equal to 0. To solve for C, since P is a point on that line, let me substitute that here. So for P, meaning 3 and -2, so you have here 6 times 3 plus 1 times -2 plus C is equal to 0. That's 18 minus 2 plus C is equal to 0. 16 plus C is equal to 0. So our C is -16. Okay? Therefore, our equation is AX plus b, in form ax plus by plus c is equal to 0 is 6x general form plus y minus 16 is equal to 0. And what is the purpose for that? We need one more point in order for us to graph a line containing point P. So you can just simply use the x-intercept. Let x be equal, y be equal to 0. That's actually for your x-intercept. Again, this is not necessarily needed. Allow me to continue. So we have here 6x, or if it's, let me see if 16 cannot be included there. So I'm going to use 6x plus y minus 16 is equal to 0. That's 0, right? 0. 6x is equal to positive 16. So x is 16 over 6, or you will have 8/3. Therefore, our x-intercept is at 8/3 and 0. So the other point, 8/3 is actually 2.67, so somewhere here, and 0. This was our 8/3 and 0. Our x-intercept of the line. Together with point P, this is now our line. Again, let me do it again. This would be our line, together with point P. So, this is where our point X would be reflected. Unlike earlier, which probably our line could of course be like that. So our reflection could just be until here, right? But since our graph is now clear, so our reflection is somewhere here. Its location is in the fourth quadrant, positive and negative sign. So you'll be guided by our result later on. Okay, that's our guide. Now let me return now to this as the meat of this. So for those of you who have skipped, you might see some scribbles here automatically. Don't worry about that. If you would like to see how it was done, you can always review the video. So for our reflection, the reflection, let me use other color. The reflection of x along line L is x minus twice x minus p, and then the normal vector, unit normal vector specifically, the inner product of that times the unit normal vector. So our x is again this one here, -1 and -5. So -1, -5 minus 2 times -1, -5, and then our p. Okay, so it just so happened that I have a fraction here, but nevertheless, it could still be used. 8/3 and 0. The unit normal vector, going back here, 6 and then 1. So you have 6 over square root of 37 and then 1 over square root of 37. Unit product of that would be, the inner product of that would be multiplied to your unit normal vector, same value. Okay, so let me continue. This would be -1, -5 still here, minus 2 times combining this component wise. So -1 minus -8/3. Take note that -1 in terms of 3 is 3, so -11, right? -11/3. So again, because -1 is -3 over 3, so we're going to have minus 8/3, so -11/3. Okay, please try to review some basic concepts as to that. So let me continue. This is actually -11/3, and for the second component you have -5 minus 0, so -5. Okay, this would be paired with 6 over square root of 37 and 1 over square root of 37 for the inner product before multiplying another unit normal vector here. Again, our unit normal vector has a radical expression in the denominator. Please not be confused with that. Later on, there will be a process that will actually simplify that. So this is actually -1, -5 minus 2 times. The inner product is when you multiply the components and you add. So -11 times 6 is -66. But since you have 3 here, okay, 3, 6, that's 2. Okay, 6 divided by 3 is 2 times 11, -22 over square root of 37. The other one, -5 times 1 is -5 over square root of 37. You add them. Then the result for that is, parenthesis, 6 over square root of 37 and 1 over square root of 37. Okay, so we still have -1, -5. Again, please be guided that the reflection is on the fourth quadrant. Our target is to make the x value positive. So this is -27, right? -2, -27, that's -22 plus -5, square root of 37. That's already scalar, times 6, square root of 37, 1 over square root of 37. So next, just multiplying these two first before the unit normal vector. So you will have -1, -5, that's plus 54 if I'm correct, 2 times 27, square root of 37 times the unit normal vector. At this time, you would see that our denominators would then be simplified because both denominators have square root of 37. Allow me to extend here. So you have -1, sorry for that, let me use other color to differentiate the steps. -1 minus 5, you have here plus, okay, this time 54 times 6 is actually equal to 324 over now 37 without the square root, because again it would be simplified. So plus, the other one is 54 times 1 is 54, then you have your 37. So basically you will have -1 plus 324 over 37, and the second component -5 plus 54 over 37. The result for that is our reflection of point X along line L. So you can have here -1 plus 324 divided by 37. So you will have here 287 over 37 positive. Check. How about for the Y? You have -5 plus 54 divided by 37, or a fraction form of that. So you will have here -131 over 37. Negative, check. So we can see that our graph earlier is really accurate, and now the location for that would be determined further if you would like to use values in decimal notation. Allow me to finish this here. This is our reflection, right? This is the reflection of X along line L. Let me remove other scribbles. So it's 287. Let me check. Divide by 37. It's actually 7.76 something. So for the x-axis, 3, 4, 5, 6. Again, 1, 2, 3, 4, 5, 6, 7, 8. So 7.7 something is somewhere here. So almost 8. Let me use other color. Somewhere here along this region. As for negative 131 divided by 37, it's actually negative 3.54. So we have here negative 1, 2, 3, middle somewhere here. So connecting them, this is our location. And as you can see from point X and that point, they are actually forming a perpendicular line there. So basically, using our graph and those all of these illustrations and the formula itself, as mentioned, you can go away with graphing, but the graph will also try to verify your other concepts and the result if they are correct. So this would be the last example for solving the reflection of a point along line L, but not necessarily the last on reflection, because there will also be double reflections and other forms of reflections, even translations and glide reflections, so on, in our journey in discussing analytical approaches to modern geometry. Thank you very much for watching.